Section 17.2, electric force. The objectives today are going to be use Coulomb's law to determine the electric force present on a particle that's charged and to compare the electric force with the gravitational force, their relative magnitudes. First, Coulomb's law says the following: the electric force felt by a charged particle or between two charged particles is equal to Kc times Q1 times Q2 all over R squared. Now, Kc is called the Coulomb constant, and its value is 9 times 10 to the 9 Newton meters squared per Coulomb squared. Let's take a quick look at this and notice right away that this formula is clearly analogous to our gravitational formula. We saw G m1 m2 over R squared. So we're going to see similarities in solving these equations, so this should be an easy equation to rearrange because we've already done it here. There's our constant, there's our constant. Particle 1, charge. Particle 2, charge. So if we have a negative and a positive charge, we get a negative answer, and there'll be an attractive force. If there's two positive charge, it's a repulsive force. That'll be a positive force or a positive answer. R, if we remember, from the gravitational force, was the distance from center to center. Now, for particles that are tiny, we're not even going to consider them having any radius, so we can say just the distance between them. So R, again, will be the distance between them. We're not going to include the radius of each of the particles, so just the gap between them. So here we have to worry about adding in the radii from each planet if we looked at planets, but here we're going to be looking at small particles whose radii are negligible. Example 1 says, using the table below, determine the electric and gravitational forces experienced between an electron and proton of a hydrogen atom if the average distance between them is 5.3 times 10 to the negative 11 meters. So let's take a look at what we've got. We've got our electron and proton and neutron. We've got the charges on them. Again, the elementary charge, the charge of an electron. We've got the mass of an electron, the mass of a proton, the mass of a neutron. We're going to need this for the gravitational force. We're going to need this for the electric force. Here's our R value in both cases, and we have our constants. So let's go ahead and proceed through this problem. So first, we want to determine the electric force, And we know that electric force is Fe, and that equals K, which is 9 times 10 to the 9, and that units again of Newton meters squared per Coulomb squared, times Q1, well, that's the charge on the first particle, that's the electron, times Q2, which is the proton, all over R squared. Well, R was the distance from center to center, or the distance between them, rather. In this case, happens to be 5.3 times 10 to the negative 11 meters. And that quantity is squared. Take a look at your units right away. Notice that they do cancel. Coulomb squared cancels here. This is going to be meters, but it's going to be squared. That cancels that meters squared, leaving behind only newtons. And we're looking at a force, so it makes sense. Plugging in these numbers and calculating, we get an electric force of negative 8.2 times 10 to the negative 8 newtons. So a very small quantity. Again, a very small quantity here. But let's take a look now at the gravitational force that's felt. If you remember, gravitational force is G, which is 6.67 times 10 to the negative 11, times M1, which is going to be 9 point, and I'm going to round this, 9.1 times 10 to the negative 31, times M2, which is the mass of a proton. This is going to be 1.7 times 10 to the negative 27, all over the distance between them squared. Calculating this quantity, the gravitational force is going to be approximately, after rounding, 3.6 times 10 to the negative 47 newtons. Now, let's take a look. This is the important part. This seems like a very small number because it's times 10 to the negative 8, which means that we're going to have to move the decimal 8 spots to the left. But take a look at here. Look at the gravitational force. This is a negative, by the way, right here. So we have a quantity that is much smaller, on order of magnitude of 10 to the 40th almost, smaller. So the gravitational force is really much less than the electric force. So what's keeping that electron in orbit there is that electric force with the proton pulling it back in. It's not really the gravitational force at all that's affecting it. Now, what we should notice is that if this sign ever turns out to be negative between on the force between two particles, it means that those particles are attracting one another, okay, because they're opposite signs. the proton and electron are opposite, so they attract, and that's because Q1 times Q2 is negative in this sense, right? So you're going to get a negative answer for two particles that are attracting each other. Gravity is always attractive, so we don't have to worry about that force. Gravity always pulls two things together. Example 2. Determine the distance between 2-point charges of 50 microcoulombs and 40 microcoulombs if they exert a repulsive force on each other of 150 newtons. So first we have to notice here that the charges are given in microcoulombs, so we have to remember that that's times 10 to the negative 6. So we can start by saying that Q1 is 50 times 10 to the negative 6 coulombs, and that Q2 is 40 times 10 to the negative 6 coulombs. We also know that the force felt is 150 newtons, and this is a positive value here because we're going to be multiplying two positive charges together. So looking at our formula, Fe equals Kc Q1 Q2 over R squared, we can see already that we're going to have a positive times a positive, thus we have a positive force. Okay, that makes sense according to our formula. So we're trying to figure out the distance between the 2-point charges, so we're looking for R. So let's switch these two here and then solve for R. So it becomes R squared equals Kc Q1 Q2 over Fe. But we'll take the square root of this, and that will get rid of this R squared and just make it R. So if we want to solve for R, we just have to plug in. We have 3 of our givens right here. Those will get plugged in here. And then Kc, if you remember, is 9 times 10 to the 9. And the units are newtons, meters squared per coulomb squared. So if we go ahead and plug in at this point, we'll end up getting a value for R in this problem of 0.35 meters, around 35 centimeters. So these 2-point charges in space would be about a third of a meter apart. Some main ideas that we've looked at so far concerning electric force. First, it's a field force, so there's no contact involved at all, like gravity. So these occur at a distance. That's where the R comes into play. There's no contact like, if there were contact, it'd be a force like friction. Its formula is analogous to that of the gravitational force, and we saw that before. The formula, remember, Fe equals K Q1 Q2 over R squared is the same as, or analogous to Fg equals big G M1 M2 over R squared. They can repel or attract, so the force can be a force that's pulling the other charge point in or pushing away from it, whereas the gravitational force can only attract. And then finally, it's significantly stronger than the gravitational force on a molecular level, and we saw that with the proton and the electron example. Example 3 now says that 3 charged particles are arranged in a line. Let's think about this. We have a line here. It says that particle 1 is located 3 meters, or 0.3 meters to the left of particle 2, which itself is 0.2 meters to the left of particle 3. So it means that particle 3 is all the way on the far right. We'll call that Q3. Then particle 2 is somewhere in here, and this is going to be called Q2, and we know that it's, 0.2 meters to the right, so this distance here is 0.2 meters. And then the next particle, particle 1, is out here, and that's 0.3 meters to the right of particle 2. So altogether, this is a distance of 0.5 meters here. We know that the charge on particle 1 is negative 8 microcoulombs, or negative 8 times 10 to the negative 6 coulombs. Charge 2 is going to be positive 3. That's times 10 to the 6 coulombs, negative 6 coulombs. And then charge 3 is going to be negative 4 times 10 to the negative 6 coulombs. Again, getting rid of the micro by multiplying by 10 to the negative 6 in all 3 of these cases. So Q1, Q2, and Q3 now. Now, the question becomes this. Determine the net electrostatic force on particle 3. So we're trying to figure out the force on particle 3. So we have to think about what's happening here. Well, particle 3 is a negative charge. A negative and a positive, those attract. So positive 3 is going to get pulled to the left due to positive 2. So there's going to be a pull on this particle. Okay, and you're going to see where we're going with this with our free body diagram in a minute. And then if we take a look next, we say, all right, well, let's look at particle 3 now, particle 1. These are the same signs. They're both negatives. So they're going to repel. So particle 1 is going to push this one away, actually. We're trying to find the force on particle 3. So what is this feeling? It's feeling a pull to the left from particle 2, but it's feeling a push to the right from particle 1. So we'll draw that in red. So that's going to be a push this way. So what we're going to really do is isolate this region right here and take a look at the free body diagram. And the way to do that is just to write, here's particle 3, and it feels a push from particle 1, so the force on particle 3 from particle 1. And then it's feeling a pull to the left, a force on particle 3 as a result of particle 2. Now notice that by doing what we've just done, by associating repulsion and attraction of these two based on the signs of the different charges, we've already taken into account the negative-positive issue that we'd have with the formula. So when we're calculating our forces between the particles, we don't have to worry about any of these negative signs anymore. We already took into account the direction. And then we're going to look at the overall result of the net force acting on particle 3. So if F31 turns out to be bigger than F32, it's going to be a net to the right, which means it's going to push to the right. This push would overcome this pull. But if this ends up being F32 bigger than F31, then the net force is going to be the left, or a pull to the left, which means this pull would overcome this push. So we'll see which of these two numbers is larger to figure out which way the actual particle will feel pull. But again, we've already taken into account the negative signs for each of these. So now we're going to calculate without those negative signs. Remember, Fe equals K. Now, in this case, we're going to first look at, let's find, instead of Fe, let's write it as F31 or F32. Let's call this first one F32. So that's going to mean we're going to put Q3 and Q2 here. So Q3 is going to be here. And again, I'm dropping the negative sign there. And here's going to be Q2. And then the distance between them, and the distance between them is 0.2 meters. And that's squared. And again, that distance is from up here, 0.2 from earlier. That's going to be F32, and what we get as a result of that calculation for F32 turns out to be 2.7 newtons. Okay, so it's going to be a pull to the left of 2.7 newtons. So really this is going to be a negative sign in a sense, but we're going to apply the negative sign when we look at our free body diagram. Similar to how we drop the negative sign on little g when calculating the weight, because the weight is already acting down, so we draw the vector acting down, giving it its negative notation already. Next, let's find F31. So this is going to be 9 times 10 to the 9 again. Now we're going to still use particle 3, 4 times 10 to the negative 6. But now we have to multiply it by particle 1, the first part, which was, it was really negative 8, but we're going to say 8 times 10 to the negative 6. Because again, we already took into account the negative sign. And that's over the whole distance squared. Well, the whole distance is the distance from particle 1, which was here, and particle 3, which was here. So if we scroll back up to see that, we'll see that this entire distance here is the distance between them. 0.2 plus 0.3 is 0.5. So that's what our number here is going to be, squared. And that turns out to be a value of 1.2 newtons. So at the end of the day, what we're noticing is this. F32 is bigger than F31. So the pull to the left is bigger than the push. So in essence, what we have here is this pull from particle 2 pulling it to the left is greater than the push it's feeling from particle 1. And it's probably because they're at such a long distance, right? It's at more than double the distance, so the effect is much less. We could see that because look at the numbers. You would think this would have more of an effect than this one, but because it's at a further distance away, it's not having as much of an effect. So this pull is overcoming this push. So if I were to draw the net force on this object, it would be an overall force to the left. Again, thinking of this as 1.2, and this over here was 2.7, well, it's going to be a net force to the left of 1.5 newtons. So we could say that the net electrostatic force is negative 1.5 newtons, or we could say it's simply, as we see here, 1.5 newtons to the left. So it's a net pull to the left on particle 3.